Okay. So hello everyone. So my topic is about the seamless CS prediction system that is developed based on the AWI-CM 3. Firstly, let's have a quick glance on what kind of model we used. So we're using AWI-CM 3. Yes, the AWI-CM 3 has an ocean model that is called FISM 2. So FISM 2 is a finite volume model with unstructured mesh. So you can see that you can have different horizontal resolutions in different spaces. Oh, sorry. Yeah. You can see that in different areas, different regions, we can have different resolution. And currently, the culture mesh, we are using the culture mesh. The culture mesh has a relative high resolution in the tropical regions and also in the polar regions, both in the Arctic and the Antarctic. But in the subtropics regions, the resolution is around 100 kilometers. For example, in the Arctic and Antarctic, we can see that it's around 25 kilometers. And for the atmosphere model, we are using the OpenIFS. So OpenIFS is an open source version of the IFS that is used in ECHAM. So we need a license to use this model, but can be easily obtained. So the current resolution we use that has 6 layers in the vertical and it's around 100 kilometers in the horizontal. And we use the coupler that is called OEC3 MCT coupler to couple the atmosphere model and the ocean model. So yeah, okay. So I will introduce you the technique about the seamless CS prediction system. So currently, we have 30 some members, which means that we have 30 AWI-CMs. We have 30 climate models, and because the online feature of the PDAF is implemented in AWI-CM 3, so therefore we can do the online data assimilation, and that has 2 advantages. So one is that we do not need any restart after data assimilation, so we can directly redistribute all this information through the memory. And the second one is that we can do the strongly and weakly coupled data assimilation, just use the same framework. So after 1 day's integration, we get to do the forecast. At that time, we need to collect all these observations that are available at that time, and we do the assimilation just on one AWI-CM model. And then this the CPUs, the cores for this one AWI-CM that does all this analysis. After that, it will redistribute all this information back to all these AWI-CMs. So actually, this is the cycle of the data assimilation procedure, and we do the daily assimilation every 3 months. So we can do the forecast just starting from the analysis. So we can get the raw forecast now, but due to the systematic errors always observed in the climate models, we need to do the forecast calibration. So currently we are using the LES-TKF filter that is coded in PDAF, and the state vector is constructed by CS concentration. This is CS thickness, the 2 components of the CS drift, and the sea surface height, the three-dimensional T temperature and salinity. Then the observation vector is constructed by we can get the operational CS concentration data, and also we can get the the freezing season CS thickness data, and we have the OCSF CS drift data. We can also have the along track SSH and the SSIS data. We did the simulation of the UKM OST data, also the TS profile data that is from the IN4 data. And first, we need to check whether this assimilation works properly. So we plot the MSE of the CS concentration relative with respect to the assimilated data. So that is this plot shows the MSE reduction of the CS concentration. We get different colors for the Arctic and also for the Antarctic, but both it shows that a very big reduction of the MSE, and that is what we want. And we also check the SST. You see that the blue curve is the blue line is for the SST, and this is the analysis result of the SST. We also get a very big bias reduction, and this is the green lines are for the sea level sea surface salinity. That the reduction is also obvious. So it means that currently, at least for these fields, the simulation works quite well. And then we also check we check the basin scale MSE of the vertical temperature and the salinity profiles. So we do this. We calculate the MSE with respect to the world ocean. Actually, this is all this observation that's gathered here, and we do the average to get the WOA18 data, and for each oceans we calculate the MSE. So we can see that in the Atlantic Ocean and the Pacific Ocean, the Indian Ocean, and the Arctic Ocean, and also for the salinity profiles in these oceans, we all get very, very obvious bias reduction. So the orange one is the control one, and that is perturbed using, that is added by very small perturbations into the initial temperature and the salinity fields. So that means the control run is also an ensemble run. So the blue curves is for the data assimilation run. But a very interesting thing is that we found that in the Southern Ocean, although we get very significant bias reduction in the surface, but in the deep ocean, we do not really have a very significant. We have even worse results actually. So that means that maybe you know that the covariances that we use, you know, that based on the surface states and also in the deep state are not very good. I didn't look into deep into this currently, sorry. But and also for the Southern Ocean, we also found the desalination of the salinity here. We see that the salinity, the MSE of salinity becomes even worse. So from all this assimilation results, we get the analysis field, analyzed field, and from the analyzed field we do the forecast. For each year we do forecast. So we start the forecast from January 1st, April 1st, July 1st, and also the October 1st, and for each experiment lasts for 1 year. So actually, if the target month is April 2004, actually we have four forecasts that have 4 different lead months. So here it has lead months of 0 actually. It's half a month actually, and for this forecast it has a lead time of 3, 6, 9, and when you check the sample spread of the forecast, so we are taking the SST as an example. So this is the global mean ensemble standard deviation of the SST. Sorry, I forgot to mention that the ensemble spread here we are using we are we are using the ensemble STD as the ensemble spread. So we get the very initial ensemble spread that is very low. We see here, but the top figures is after 1 year's integration, we get very high ensemble spread that's almost very close to the internal variability of the client models. So we can see here. So for example, if the forecast initialized in January, we see that the initial standard deviation is about 34% percentage of the final STD. So actually, it means that the ensemble spread drops very fast to the free run, and I think that is expected, because that is what we can always find, you know, in all these climate models. And we also check other states, for example, the CS concentration, the CS thickness, and the sea surface temperature that I just showed, and the sea surface salinity. We all see such kind of ensemble spread growth. And one more interesting thing is that, you know, if we say the snow thickness and the sea ice drift, the two components of the sea ice drift, we didn't really see this such kind of thing. That is also expected, because, you know, we do not really do any snow thickness assimilation, but actually we did do the sea ice drift assimilation, but we did not really see any influence of the assimilation because of the very small inertia of the sea ice drift, and maybe very small memory of the sea ice drift. And after that, you know, we have the raw forecast. Then we need to do the forecast calibration to remove the systematic errors. And so the calibration method we used, that is called a trend adjusted quantile mapping method. So this method is developed by Dirksen in 2018 in GC, and basically we get the trend adjusted CDFs, and we get the historical observation CDFs. We also get the red one. This is for the historical model CDFs. For example, if we have the CS concentration located here, X here, then we can get the historical forecast here, and then we remap this value to the observations by the inverse of the CDF of the historical observation CDFs. So this is a very straightforward, I think. And I would like to note that all the results below are all after the forecast calibration. So the first one, we need to check the CS concentration climatology forecast. So the rightmost column shows the OSISAF climatology average over 2011 to 2019. We see this is observations, and we want to calculate the difference between the forecast results and the observation result. We see that, you know, in the Arctic oceans, we have a larger bias in the marginal ice zones, and that becomes even evident, you know, in September. We see that all over the Arctic we get positive errors, but this is not the case for the Antarctic. We see that in the Antarctic, the errors are really spatially distributed. We see that here we get negative errors, but here we get positive errors. That is also for the September. I think this is because normally the sea ice in Antarctic is more difficult to simulate than that in the Arctic. So when they check another very important metric, it is called it is the MSE of the CS concentration forecast. So here we compare our results with the observation. That is, for example, the OCSAF observation forecast. That means that we use the historical values as the forecast. So, for example, if we want to get the observation forecast for in 2018, we just take the average of 2011 to 2017, and we use this value as the forecast for 2018. So this is the observation forecast. But that is interesting to find that, you know, all our forecasts only with lead time of 0 to 2 months can really beat the climatology forecast. That is to say that if we have a forecast that is longer than 3 months, we can just use the historical observations as a forecast. It performs even better, and that becomes even worse in the Antarctic. We see that even we use such kind of forecast calibration method, the forecast, you know, with lead time of 0 to 2 months cannot really. It has the value of 0.17. That is even larger than the historical observation forecast. And another metric is the so-called integrated ice edge error. So it means that we just sum all these areas that observations mismatch with the forecast, and this plot shows the climatology forecast as what I said before. In this plot, the climatology forecast, we can see here. It generally it has a smaller error, you know, in the Antarctic, but sorry, it has smaller error in summertime in the Antarctic, but it is just reverse in the Arctic. So below two figures shows our forecast, shows the differences between our forecast and the OCSAF climatology forecast. But generally, we can see that the forecast in the Arctic performs even better than that in the Antarctic, and we see that it is very obvious that only the forecast initialized in July that performs even better than in other months for the Arctic, and that is not the case in the Antarctic, because we find that in the Antarctic that the forecast that initialized in January that performs even better. We see here, we take this as an example. You know, for example, if we want to get the forecast in April, you know, we can have 1, 2, 3. We can have at least 3 months. 3 months lead time. We still have very close to the climate to the observation forecast. But for the forecast that is initialized in April, we can only have 2 months. Yeah. And then it comes to my summary. So basically, I just showed a similar CS prediction system that's recently developed based on IFCM3 in the RV, and we found that in our forecast, the CS forecast in the Arctic have a higher forecast scale than that in the Antarctic. And one more thing that I want to say that our system does not really constrain any atmosphere model. So basically, the model is totally free. So that brings some errors into the forecast. So I would say that to also constrain the atmosphere and also try to using a better calibration methods. I think it is very important to improve the Antarctic forecast. And currently, in our group, there's some people, they are working on the also on the data assimilation in the atmosphere, but they have different approaches. One is by just using the strongly coupled data assimilation, as I just said before. You know, they just put the atmosphere states and ocean states and the sea states in the same state vector, and also another people, they are just do the very simple data assimilation method. For example, using nudging, they just nudging the reanalysis results to the atmosphere model and to the forecast. Yeah, we will see. Then it comes to my end. Thanks very much.
Thank you, Longjiang, for this very nice talk. I think there are no questions so far at the Etherpad. But I think also the time is nearly over.